day.
That helps with good energy, Tahir.
I think we need at this point of time.
Good points. Good points, Gord.
I think at this point of time, as I said yesterday, I feel the way you feel exactly. We, and I say we, not I or you, we have been working so hard for the last 12 weeks, and I want to keep the spirit high. I want to, carry on until the last, while everybody still has willing to come and attend my 2 hours class. And again, if it needs from me to give you 3-4%, why not? Let's do it. Okay, no big deal. It doesn't come from my salary. If it comes from my salary, I will have to think about it maybe several times before I do that. Okay.
See,
Uh, excuse me.
that's why we love you.
Okay.
You're very generous.
Okay. Thank you. Okay, so let's go ahead and see what do we need to take here today. So uh, we for the last two classes, I know it was kind of very dry, very theoretical, but hopefully things will get a little bit clearer today. So in column design, and we know that column, they are vertical element in the building, and the main force that acts on the column is axial force. Let's agree on that.
Hey, Tahir, there's not sharing your screen if you are trying to.
Okay, thank you, sir. Okay. So as I said, we've been working on columns now for last couple of classes. Things were very theoretical, very dry. We brought up some concept that we need going forward. But let's agree on this concept. The columns are vertical members in the building. And those columns mainly, they support axial load compression. One more time, the columns are vertical element in the building, and the main force acting on those column is a compression force. And probably by now in your CVT live, you know that if you subject a member under axial force, there is something is going to happen, which is called buckling. And I know that buckling, this word is not new. You study buckling in your steel course, maybe strength of material. So you are completely aware of the meaning of buckling, which is an instability that happens to a member under axial force. Really, what governs the buckling is something called slenderness ratio. When the member is slender, it suffers much from buckling. When the member is, I would say, chubby, big, compared to the length of the member, then it suffers less from the buckling. So the way we deal with the buckling in concrete is quite different from the way we do it in steel. So the idea is the same, but when it comes to the design or taking the buckling into consideration, it is different. In steel, probably I can remind you and just remind you of what Corwin is doing. In steel, you estimate the slenderness ratio, which we typically use lambda for this value. So we estimate lambda, and if lambda is big, it means the column, or sorry, the lambda is large, then the column is cylinder or more cylinder. And because it's more cylinder, it's more prone to buckling. Why, when we design this column, we reduce the stress on the column. That's how we deal with the buckling. The more cylinder the column, then we simply use less stress for the design of this column. This is not the way that we're going to use in concrete. So in concrete, what we have to do is we start from the same idea. We have to estimate what we call slenderness ratio, which is on my screen. Please look up my screen. And this whole number here, I'm going to box it out for you. This number here It is KL unsupported divided by R. This whole term, it's called slenderness ratio. Again, one more time, if the number is large, then it is cylinder. If this number is small, it means it's not cylinder. It is chubby and will suffer less from buckling. You can see in the term there are three different parameters. Let me zoom in and show you. So there are three different parameters here. Number one is K, number two is L sub U, and then finally little r here. So the K, and every one of those is a little story, which I'll go and take you through the story. But for now, let's get the names. So the K is something called effective length factor. Because it's a factor, it has no units, huh? It is just a ratio. So it's an effective length factor for compression member. Sometimes in other literature, they call it buckling factor. And then L sub U, it refers to the unsupported. Look at the name, the unsupported length. So remember what the axial force is trying to do. What happened to the axe of the member? It will go off the center line of the member. And once you provide lateral support, it means you say, okay, no, don't go anywhere. And really, the unsupported length is the distance between where the member is laterally supported. If it's not clear, please be patient. I will show you in a cross section what do I mean by L sub U. Then finally, the little r is the radius of gyration of the column cross section, which is one of the geometric properties of the section. You guys, strength of material, you learn that there is something called the area and something called the modulus of section and moment of inertia. All of those are geometrical characteristics or properties of the section. In strength of material or steel, the way we estimate the radius of gyration is by square root of the inertia divided by the area. I'm going to write it here for you guys for your reference. So in strength of material and in steel, that's how we do it. We say square root SQRT of I divided by A, where the I is the moment of inertia and A is the area, and we get R. And you guys remember also, if you remember also from strength of material or steel, any section, it has more than one axe. For example, if this is my member, if this is my section here, let's say make it a rectangle, then there is here something called XX, and there is something called YX. Again, this should not be new. If it's new, then probably you should quit. Okay. So there is an XX. I'm gonna probably write it here. So this axis here is my XX axis, and this axis here is my Y axis. So you know that there is a moment of inertia about the I, moment of inertia about the X, and they are different. And so that's why, because there is something called the IY and IX, and there is something called the I maximum and I minimum, the R value is not the same, is not only one number. For the same section, you can find Rx, which is, so how much is my Rx? Is not very difficult. So Rx is equal to square root of Ix divided by area. And again, if you want to see what is your Ry, then all you have to do is you go back and say, you know what? The radius of gyration on the Y direction is simply the moment of inertia about Y-axis divided by the area. Okay? Now, this is how we do it in strength of material and steel. We do that only if the section is one material, whether wood, concrete, steel, as long as the whole cross section is one material and it's uncracked, then I can find the radius of gyration from this equation. Now, is that our case? Is that our case? We're designing reinforced concrete columns where it is combination between concrete and steel. That's why estimating the radius of gyration is not as easy as steel or wood. So anyway, I'm gonna make it simple for you. So in our class here, every time you see a rectangular section, then you just multiply the dimension of the section, multiply it by 0.3, you get the radius of gyration. And if the section is circular, then you multiply the diameter of your section times 25%, you get the radius of gyration. Remember the units? So the units are, please pay attention to this. The L is an unsupported length, which means the units are millimeters. And the radius of gyration is, it's called the radius of gyration. Look at the name, radius of gyration. So it looks like it's a distance as well. Even from the equation, I is millimeter to the power 4. And if you divide it by the area, which is millimeter square, and you take the square root, then the Rx or the Ry will be in millimeter. So let me ask you, if this is millimeter and this millimeter, and I said a few minutes ago that the K is just a ratio, it's a factor. Let me ask you, the slenderness ratio, does it have any units? Please answer if you can.
It's
No.
unit.
Unitless. Unitless.
It is unitless. Thank you so much. Slenderness ratio, it is unitless, dimensionless. Okay, let's move on to another very important concept, which is called sway frame and non-sway frame. And please be patient when I discuss with you. Please be patient, okay? So when we build a building, we can build it same as the picture on the left, or maybe we can do it as the picture on the right. The whole problem is about lateral loads. So whether the left or the right columns, they can support the vertical loads. The problem is lateral loads. And I ask you, what do you mean lateral load? Can anybody in the class tell me what do I mean by lateral loads?
There are loads that causes by the winds or earthquake.
Thank you so much. Yes, lateral loads are perpendicular to the gravity loads like earthquake and wind. Now, what happened is we want to make our building stay and stand to resist the wind and the seismic. How can we do that? We have two options. We have two options. Option number one, which is the most common one. The most common one is what you see on the picture on the right. What you see on the picture on the right, we provide a member, an element in the building that takes care of the lateral loads. You can see very clearly in the picture to the right is anyone can observe what exactly resisting the lateral load on the picture to the right.
The shear wall.
Thank you, sir. It's the shear wall. So yes, the shear wall is the stiff element in your building that takes care of all the lateral loads, And that's why, because the shear wall takes care of all the lateral load, you will see column in this case, they do nothing for the lateral load except the exterior column if we support what they call it, the glazing on the column. But if we simply support the column on the floor, it means the column will get absolutely nothing for lateral load. Okay? Hopefully this is clear. And by the way, so you know, 99% of our building, we do it the one on the right. If you have been in Calgary here for the last few years, and you commute in downtown and you've seen those high-rise building in downtown, and you notice how they build them, what they do is they have a big shaft in the center of the building, and this shaft is simply the core of the building that simply restrain everything from the motion laterally. And during construction, typically they take the shaft and they advance in the construction of the shaft before even the floors get in. First, then floors next. Okay. Now, this kind call it non-sway frame. So if we add shear wall, and by the way, shear wall is equivalent to bracing. So whether you place bracing or shear wall, both of them We call them non-sway frame, non-sway frame. Sometimes, because of the architect, sometimes we cannot add those sway like shear walls or bracing. So then if we cannot add a shear wall or bracing, how can we take care of the lateral loads? Any help? Do you want me to say it again? So
Yes, please, sir.
in 99%, we're allowed to add a shear wall, and then done. Shear wall can simply take care of all the lateral loads. So my question for you is, what if we cannot add shear wall for a reason? What can we do? Because if we simply don't provide an alternative, then simply as soon as the building is hit by wind or seismic, the building will collapse. We need to make sure that our
Yep.
building can resist lateral loads.
You have to
Bracing?
put bracing, yeah.
I said, guys, listen, I said bracing and shear walls are equivalent. Both
Oh.
of them, they fall under the right picture, non-sway frame. Okay? Here is, because maybe it's difficult for you, so I'm gonna tell you what happens if we're not allowed to place a bracing or a shear wall. What you have to do, you must go with a frame concept. So what is the difference between a frame and beam column? Simply the connection. What I'm pointing right now, all these connection between columns and beams must be a rigid connection. Rigid. All these connections must be a rigid connection. It means it can carry moment. How about the one on the right here? The one on the right here, it simply does this. So this is your beam, and simply your column is here, and simply we don't have to carry any moment. We simply assume that this point here is a hinge. It means if the beam wants to rotate, then the column is okay, go ahead, do it. I'm not gonna follow you. But on this picture on the left, once the beam trying to rotate, then the column will say, okay, I'm here, I'm gonna resist, I'm gonna restrain you. And this connection, it makes your building is able to resist lateral loads only if the connection between the column and the beam is rigid connection. Are you following?
Yeah, we're following.
Okay, so now, as I said, why 99% of our building that we construct follow the concept on the right side, and only 1% probably will follow the one on the left? Is because the one on the right is easy to analyze, easy to construct, while the one on the left is a hell to analyze and hell to build. Because what happens here, when I zoom in, if you think about this connection over there, you have to make sure that this connection carries moment. And probably with Corwin, you will understand how can we make a connection carry moment. So we have to have some gusset plate, and we have to have some bolts and stuff like that, while it's way simpler to make it a hinge. Not sure if you already learned that already. In terms of concrete, the column bars will have to extend and go into the beams. Not only like I showed you before, so the column bars, yes, will go a little bit inside your beam, but not necessarily will bend and go to, enough distance into your beam. At a very high level, without further ado, without more details, the difference between the left picture and right picture is the connection. This connection here is simply looks like this in our analysis. In our detail, in our construction, it's a hinge. We don't carry like load from beam to column. How about the one on the left? No, we have to make sure that the column beam connection is so strong, and that's how what enables this building here to take the lateral loads. Anyway, in our class here, we focus on the most common one, the 99%. So in our discussion, we will focus on non-sway frame, non-sway frame. Okay, so another discussion, which I am 100% sure that this discussion is not new. It has to do with the K, which is the buckling factor, which is if I have a member and this member is of length L sub U, so here is the length of the member L sub U. Now, what is exactly the length that the member can buckle on? It depends, and please, I'm going to make it clear. It depends on the end conditions. It depends on the end condition of your column. For example, if I make and design and detail the end connection of my column to be a hinge, it means there is no restraint of rotation of this point, and there is no restraint of rotation of this point. And this means if I apply axial force, my column will buckle along this curve here, okay? And that's why in this case, your K is equal to 1, because the buckling length is equal to the L unsupported, okay? Now, how about if I do something, I hold my column with a moment connection to a rigid beam, and this rigid beam will stop the column from rotation. What happened is here, please look at the deformed shape. You see the buckling length, which is this guy is called the buckling length, is not equal to the full length or L unsupported. It is a ratio of it, and here it is 0.5. So between these inflection points, I'm going to point out from this point here to this point here, this is simply a 50% of the length of the member. And that's why K is equal to 50% or 0.5. When the two ends are fixed. Now, I guess you can imagine what happens if one end is fixed and one end is hinged. What do you think? What is the range of the K, or what's the value of the K? Any guess?
0.75.
But it is 0.7. So when you fix one end, then the other end will be a hinge. It will be a 0.7. Now, I'm going to give you a more complicated question. What if, because remember, I'm going to tell you, to be honest, whether this state or this state, those are pure theoretical, which means making a joint a pure hinge completely rotates freely, or make it 100% fixed. I can tell you both of them, they are pure theoretical. So really the one that is more realistic is on the one to the right side, on the right side. So on the right side here, we have a column, and the column is connected to something on the top, but this something on the top, on the bottom, it has somewhere in between being fixed or being hinged. It doesn't allow the rotation 100%, and it doesn't stop the rotation 100%. And in this case, the K will be anywhere between 0.5 and 1. This discussion is a little bit more complicated, because in order for you to find the exact K, you have to find the stiffness of those members connected to your column, all these members. And with the stiffness, I'm not sure if you remember this name, sometime in my course I said there is something called I divided by A. You cannot, it's like, it is the length, I divided by L. We talked about this before in our course. If the member section is big, then it's more stiff. Also the length, when the member is so long, it is less stiff. Anyway, on a very high level, without any deeper details, to get the exact value in this case, then you need to estimate the stiffness of all the members coming and connected to your column. I'm going to make it simple for you. In our assignment, I'm going to give you the K. I'll give you the K. And to be honest, what is the safest number? What do you think? What is the safest number in our design?
0.7.
Safest number, safest.
Oh.
One.
If you really want to, if you don't want to bother by estimating the exact value of the K, then let's assume that the end of the column can rotate freely, and that's why the K is equal to 1. By the way, so you know, in most cases the K will be anywhere between 1 and less than 1. There is only one case where the K will be more than 1, which is a cantilever. If you have a member that it's fixed only from one end, for example, like this, like let's say I have here a column that is a cantilever column. which is not really very common to make a cantilever column. It happened for pylon signs and flags. Those are a cantilever column. So in this case, when you think about the buckling shape, guess what? This is how the column will buckle. And if you want to come up with the full sine wave, this is will make you that L buckling will be twice as the length of the cantilever. Very, very uncommon, very rare. In our building, our columns will be tied at the bottom and at the top, and the K will be 1 or less than 1. Are you following?
Yes, sir.
Yep.
Okay, now here is a real business. We're going into the real business. Please pay attention. Real business is coming. So as I said, the way we design the column for buckling in concrete is completely different on how we design the column in steel for buckling. So here we go. In concrete is even way, way easier than steel. Way easier. In concrete, it is either we ignore the buckling or we take the buckling. There is no third option. You take the buckling into effect or you completely ignore it. Unlike steel. In steel, every steel column, you must take the buckling into effect. In concrete, it is not like that. In concrete, you either take the buckling into consideration or not take it and ignore it. Based on what? Based on what you see on my screen. Please pay attention. So in concrete, really, it comes down to the following. You must estimate this number here, okay? I'm gonna box it out. I'm gonna give you all the details later on, but you must estimate this number here. And this number inside the box is your lambda maximum. Can anybody remind me with the name, what is lambda? Anybody still remember what is lambda? I mentioned already lambda.
Slenderness ratio.
Thank you so much. Thank you so much. So really, what you have to do here is you estimate the maximum value of lambda. And then you estimate the lambda for your column. If the lambda for your column that you're designing happens to be less than lambda maximum, we're okay. It means your column is a short column and we don't have to worry about buckling. The column is big enough, is chubby enough to neglect the buckling. And if your lambda for the column exceeds the lambda maximum by this equation here, with the number that I box out in red, it means your column is cylinder, and no, we have to consider the buckling in our design. Now, all it takes from me right now is to explain for you how do we simply estimate every element in this equation. Now, I guess nobody wants to know what's 25. Again, 25 is a number. Who did this one? There should be a research. Somebody did some modeling, but we as a designer or engineer, we just use it. So 25 and 10, those are numbers. I don't have to explain for you where they come from because I have never myself even know where they came from. This is the come from the code. There is some research. Somebody came up with this value. So 25 and 10, those are constant, don't change. Okay, now I'm gonna leave M1 and M2 for now. I'll come back in a minute, but now let's go back down to the denominator. What is P sub F? Do you guys remember that I said in beams we use M sub F, and in shear design we say V sub F, which is shear factored shear. In this case, what is P sub F? Any guess?
It's a factored load.
Exactly. So this is the factored load affecting the column that we're designing, P sub F. Where do we get this number? From our SAFI model. So if I have a SAFI model and I made all the load combination, in this case, we get from there the PF, which is the axial force, the factored axial force acting on your column. Now, anybody in this class at this point of time doesn't know what is F prime C? Please don't say no, because otherwise I will just hang myself. F prime C is
Compressive strength.
concrete compressive strength. That's concrete, how much it can take in compression. Now, I guess also at this point of time, I can ask, does anybody know what is A sub G? Can guess what is A sub G?
The gross area of the scroll column section.
The gross area of the column. So looks like, oh my God, that's very simple. There is only one thing left, which by now you don't know what is M1 and what is M2, correct? Are we in agreement that the only thing that stands for now is what is M1, what's M2? What do they represent, okay? So here we go, the M1 and M2, those are the end moment on acting on the column. The end moment acting on the column. Now, which one, like which is which? Always, always, always. M1 is the smallest, and then M2 is the largest moment. Okay? So every column, it has two ends. So always, always M1 is the smallest, and M2 is the largest, which means if I say that always M1 is the smallest and M2 is the largest, what does it mean? It means this number, this ratio will always be less or equal 1. Would you agree?
Yes.
Yes, yes.
Excellent. So excellent. So M1, M2 is again is a ratio between the smallest end moment divided by the largest moment, and it's always smallest by largest. It means equal or less than 1. Now, one more time, where do we get the M1, M2 ratio? It comes from your SAFI model. If you build a SAFI model, then you can find the end moments from the SAFI model. In our exams or assignments, we don't build any SAFI model. So I'm gonna give you the ratio between M1 and M2. However, the M1, M2, it has a sign. So the M1 divided by M2, not only it has a value, but also it has a sign. It means it can be positive or it can be negative. According to what? So please look at the picture at the bottom of my slide. Okay? So if the M1 and M2, they are like counteracting or opposite to each other, so you can tell here M1 is clockwise and M2 is counterclockwise. So we call this one single curvature. We call this single curvature. Not very hard to understand. Take your pen, try to bend it from each end, and you can tell, if you bend it from each end, same as the moment direction, it will take the curve dashed on my screen. This dashed curve. So that's why we call this one a single curvature. And in this case, your M1 divided by M2, it has to be positive. So it can be positive 0.6, positive 0.8, positive 0.9, and so on and so forth. Positive. How about the M1 and M2? They are acting on the same direction. You can tell M1 is clockwise and M2 is clockwise as well, not the opposite of M1. In this case, you can tell your column will take this curved shape, and it's called the double curvature. And in this case, your M1 divided by M2, it has to be negative value, which means, for example, let's say your M1 is 200, and then your M2 is 400. So in this case, how much is that? That is 0.5. But because of the direction of the moment, this will be, in this case, the ratio will be minus 0.5. Okay, now here is your final comment. I'm gonna put it here. I'll write it down. So minus 0.5, and then M1 dash M2, and then 1. Can you please read this statement? So this statement here tells you the ratio between M1 to M2. It should be, I don't have tool here to write more or equal. So please think about this one as more or equal, like this. And then M1, M2, it should be less than or equal than 1. So M1 slash M2, it has a range. It goes from minus 0.5 to 1. And this is by the code. If you have the code clearly said your ratio between M1 and M2 should be more or equal than minus 0.5. If it's a double curvature, then it's negative. It's a single curvature, it is positive. Any question for now? Any question for now?
No, no question.
Okay, so again, before I leave the slide, let's cap on this concept. Very, very simple. It looks, I know some of you maybe by now overwhelmed by the shape of the equation, but the idea is not, don't be overwhelmed. It's very simple. We're trying to find here lambda maximum slenderness ratio. Very simple. The only thing that you need to learn about it in the equation is M1-M2, the ratio. If it's a single curvature, it is positive. If it's a double curvature, it means negative value. In the exam or in the assignment, I will give you the value of M1 divided by M2. And if I mean, which I promise you I will not, then I will say the column is single curvature or double curvature, where you will have to add the sign yourself. Okay? So you can tell right now there is no super science. You have to go through the equation, and let's say you did, and this number happens to be 30. Okay, 30, and it has no units. Remember, this is your lambda maximum, and lambda, it has no units. Then what you do is you look at your column, and then what you do is you find the K, the L sub U, the R, and then compare between this lambda for your column against the lambda maximum from this limit here. Well, if it's less, great, my column is a short column and I don't have to worry about buckling. If it's not happening, which means your KL unsupported by R happens to be more than this number, like let's say 30, then in this case, your column is cylinder. Now, okay, so in our class, if you remember, like the last class, we said we talked about short column, a long column, or cylinder column, and I said we are not going to design a cylinder column. That is outside the scope of our class. Now, let's say you're solving an assignment, you're solving your final exam, and you check the condition, and simply the condition tells you that this is a cylinder column. What can you do?
Leave it.
Quit.
Because you said we're not dealing with a slender column. We're only dealing with, it's outside of our scope.
No. You're right. Maybe you're right. Maybe I'm wrong. I don't know. But here is how I want you to do. Okay. So if you run into this situation, so you pick column dimension, you try to find your KL unsupported, divide by R, and it happens to be more than this lambda maximum, then it means your column is cylinder. And Tahir never taught us how to design a cylinder column. So we will force it to be a short column. How can we force a column to be a short column? What do you think?
I think we have to like adjust our design with the AG.
Anybody, guys, following? Anybody wants to add to Jelly? My question one more time is, you are designing a column, and then during your design, you have to check this condition. The condition, simply the lambda for your column is more than the lambda maximum. Then it means the column is cylinder. But we want to finish our assignment or our exam. So in this case, what you have to do is do something that simply make the condition happening. It means your lambda for your column will be less than the lambda maximum. Look at that math, and the math will tell you. Let me go ahead and do that. Let's zoom in here. So as I said, you're trying to find this number, and this number happens to be, let's say, 32. Okay? This number happens to be 32. What does it mean? If this number is 32 and the lambda maximum is 30, what does it mean?
It means it's
Okay.
It means what, Gord?
means your lambda is too big.
And what does this mean? Like, you know what this mean? Is it short column or cylinder column?
It's a cylinder column.
Cylinder column. And I will teach you how to design a short column, not a cylinder column. Then how can you force the column to be short column? The answer is here. The answer is here. Let me ask you, can we change the K?
Yes. Yes, you can change the K through the connection.
Yeah, you need to make your beams are very strong so they can resist the rotation and makes a less K. So if you make less K, then this number will change down, will go down, right?
Yeah.
Or the other thing, probably, Jelly, you're proposing to make our building shorter, huh? So what we do is, instead of going for 8 feet clear height of your floor, then let's go with 6 feet. Because
I
this
was
will solve the
supposed to tell
problem.
you that one, but I thought like it was stupid answer.
The guys following? I'm trying to mislead you, okay? I'm saying here, we make our beams so strong. We fill our beams with lots of rebar, and we make the connection very strong, so it can restrain rotation, which means I go from K equal to 1 to K equal to, let's say, 0.6 or 0.7, okay? So that's one thing. The other thing is, no, change the floor height, because L unsupported, this number here, you will see shortly, it's function of the floor height. The longer, the taller the floor, then L unsupported will be bigger. So what you do is, somebody's coming to you and say, build for me a building with 8 feet or 7 feet floor height. Tell them, no, 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 I will make it 6. What do you think? Is that feasible?
No, not really.
Not
No.
really,
Yeah,
huh? Guys,
I-
listen, it's here. How can we make this number smaller? I would say the secret is here. The secret is here. We have to increase the radius of gyration of our column. Hopefully you're following, huh? And how we do that? The answer is here. Where or what is controlling your R? What do you think? What
your
controls the
diameter,
radius of gyration?
the diameter.
The diameter if it's circular, and the column dimension if it's rectangular or square. Guys,
Still,
the answer is here. The answer is here. The answer is, if you check this condition and the condition is not met, then what you have to do is simply change the dimension of the column. By changing column dimension, this will make your column chubby and less cylinder, and it will be a short column, and you will see this in our design shortly. Now, I'm going to say a few things before we break, which is, in our design, we will need a value called gamma, and gamma is a ratio. And please look at the cross section here. So the cross section between the end to the end, that is H, and that's the column dimension. And then between the center of the rebar to the center of the rebar, this is called H prime. The ratio between H prime to H, this is called gamma, okay? In our design, we need gamma because gamma, it represents the lever arm of your rebar, okay? So gamma, it can be, it's not super science. Here is an example for you. Let's say your column is 600 by 600, and we have 10 M ties, and we have 20 M bars. And I think also here, you can add to that one, please write it down. Cover equals 40 millimeter. I'm asking you, if I give you this information, would you be able to find the gamma? Not very difficult. Look at this, please. We've done this several times in our class. So 600 is from this point to this point here. And then if you take one cover from this side, one cover, and then one tie diameter from this side, another one from here, and then half bar from this side, half bar from this side. So finally, we're able to find H prime, which is happening here. So 600 minus 2 cover, minus 2 tie, minus 2 half bar. So what you get is 480. And if you divide 480 by 600, you get the ratio between H prime to H. Then gamma is equal to 0.8. Now, there is something called design aid, and you can tell here this will take you for a few seconds, but the code, the manual, gives you kind of alternative way to do that. So what I did is I simply copy this part from the code for you guys. So this table here, it helps you to find quickly the gamma. Let's see how can we do that. So you can tell here, this column gives you the column dimension. So this column here, it is the H, and starts from 250, that's the minimum, 300, 350, and so on. So where is my H in the problem? Is here. So that's 600. Okay? And what happens here? Here is your 40 cover, and here is your 20M. And what happens here? Your 20M, you go down, and right away from the table, you can find your gamma is equal to 0.8. Okay? So two options for gamma. You can do it manually, or you can use this design aid from the table. So for your information, please make sure you download every material available on the D2L. So under the column design, I already uploaded for you what you need for design aids. So I'm going to go through more of them today, but here we go. So this design aid is available on the D2L. So the table that I pointed out right now, it is over there. So there is a PDF on the D2L. Please make sure you download. Okay? And again, it's not super science. Even if you don't know how to use the table, then I guess everyone in the class by now is able to do this very simple math. Yes or no?
Yes.
Okay, so I'm going to break right now. I will see you at sharp at 2. Thank you.
Tahir,
Go ahead.